Hello, welcome to Noise Control and its Management. Today is the start of the last week of this course, and what we plan to do this week is discuss the mathematics of mufflers. Now, last week what we had introduced was this idea of a Helmholtz resonator, and we can use resonators such as the one known as Helmholtz resonator to reduce noise levels, particularly in the neighborhood of a specific frequency. But in a general sense, these resonators are used as silencers or mufflers, and there are several types of mufflers. So, first what I plan to do today is discuss the overall landscape of what kind of mufflers exist in the industry, and then we will look at the mathematics and some important design principles related to some muffler types, and hopefully by the end of this course you will have some idea as to how mufflers work and how they can be designed to meet your specific needs. So, this is what we plan to do today. So, in general when we talk about mufflers, so they are also, so mufflers are also known as silencers. And overall, in a very broad sense, there are two types of mufflers. So, you have reactive mufflers, and the second category is dissipative mufflers. Both these mufflers are used to reduce sound, but the operating principle or the working principles of these two broad categories of mufflers are different. In reactive mufflers, we rely on resonances of the system. So, what happens is that if there is a resonance, either the energy around the resonance frequency gets reflected back, or it gets sucked into the muffler and gets diverted from the main channel of the through the main transmission path of sound. So, these are reactive mufflers, and in dissipative mufflers what happens is that sound gets absorbed and it gets absorbed as heat. So, in reactive mufflers we are relying on reflections and or sucking in of the energy in a particular direction or diverting the energy at a particular frequency in a different direction than the normal path. So, these are reactive mufflers and they work particularly well around their resonance points. These dissipative mufflers, they convert sound energy into heat, and it depends on what type of materials are used in the muffler, and the nature of these materials and the amount of surface area of these materials which gets exposed to sound transmission path influences the efficiency of the design of dissipative mufflers. So, here in dissipative mufflers the important parameters are surface area and the material's absorptive property. Okay. In reactive mufflers, what is more important is not so much the material's absorptive property, we do not rely on that, rather we rely on geometry, because the geometry decides what kind of resonances will exist in the system. So, geometry and boundary conditions. What we will discuss this week is primarily different types of reactive mufflers. We will not discuss too much about dissipative mufflers, at least in this course, because of limited time available, but overall these are the two broad categories. Now, you can use these mufflers have lots and lots of applications. The most common application which we come across very frequently is in case of cars and motorcycles and automobiles and scooters and so on and so forth, where there is a lot of noise which gets emitted by the engine, and because that noise is centered around very specific frequencies. So, we use reactive mufflers which are designed in such a way that those specific frequencies are suppressed by the reactive muffler. These mufflers which in automobiles are primarily reactive in nature, but they also have some dissipative capability, because most of the mufflers in automobiles nowadays are not purely reactive or not purely dissipative, but some sort of a mixture where we use both geometry and the sound absorption property of different materials to kill noise. Now, we had discussed earlier, we had introduced the concept of Helmholtz resonator, and this is one device which can be very effectively used in a muffler to control or reduce sound around a particular frequency. Now, typically, so but then again, this type of device, which is a Helmholtz resonator, is used in the first category of mufflers, which is the reactive muffler, and we will learn how it works. Reactive mufflers based on geometry, we can classify them in two categories. One is side branch mufflers, side branch type, and the second one is inline mufflers, inline type, and then of course, you could have a mixture of these. So, what would be a side branch type of a muffler? How would it look like? Suppose I have a pipe which is transmitting sound. So, sound transmission path is in this direction. What I do is I design a muffler which branches out like this. So, this is a side branch, and this you see is a Helmholtz resonator. Now, this could be either a Helmholtz resonator or it could be just a straight pipe. That can also work, a straight open pipe. So, instead of this Helmholtz resonator, I can attach a straight open pipe, and that can also act as a muffler, or it could be also so this is a straight short closed pipe, actually a long pipe which is closed, or a short open pipe. So, this is one option where I have a long pipe which is closed at one end and the other end is connected to the tube's side, or the other option is I can have a Helmholtz resonator, or the third option is I can have a short open pipe. All these three, 1, 2, 3 can suck in sound at specific frequencies, and because these three different devices are attached to the side of the tube, this type of a muffler is known as side branch muffler. Now, the other category of muffler could look something like this. So, I have a pipe, and then I put a bigger cylinder, and then I have an exit pipe. So, this is inlet of the muffler, this is exit of the muffler, and the cross sectional area here is S1, cross sectional area here is S2, and the cross sectional area here is S3, and S2 is very large compared to S1 and S3, and then this length is L. So, we will learn about the mathematics of this type of a muffler, and this type of a muffler is known as inline type because it is in the line, in the direction of the flow of sound. Now, this type of a muffler is known as single cylinder expansion chamber muffler. But there is no reason why I cannot have multiple expansion chambers. So, what would a multiple expansion chamber look like? So, it would be something like this. So, this is my inlet, I have one chamber, then another exit for the first chamber, then I have another chamber and then the exit. So, this is my exit, this is my inlet. So, here because there are two chambers, this is known as double expansion muffler. The first one is single expansion chamber muffler, second one is double expansion chamber muffler. Okay. So, I just wanted to make you familiar with different topologies and so that you get an idea about the terminology. And now, what we will discuss, we will start discussing is the side branch type of muffler today. And specifically what we will discuss today is the side branch muffler, where on the side of the pipe we are attaching a Helmholtz resonator, and let us see how it will work. So, what we will discuss is side branch with Helmholtz resonator. Now, in this course we will not discuss the detailed mathematical derivation of some of the results we will be sharing, but some of these results can be gotten through the application of one dimensional transmission line equations, which I have discussed in the first part of the course. And if you want to go deeper into the detail, that theory which I had covered in first part of the course can be used to develop what we know as lumped parameter models of the system. So, if we do a lumped parameter model of these type of systems, we can get the results which I will be sharing with you in context of these mufflers. So, we will discuss the noise reduction properties of a side branch muffler, which has a Helmholtz resonator. Okay. So, once again, how does it look like? So, this is my pipe and I have a small pipe coming out and there is a volume. So, let us say the sound power which is flowing into the system is W in and which is flowing out of the system is W out. Okay. Then the sound power transmission coefficient AT. So, what does AT mean? It is the ratio of W out by W in. Okay. W out by W in, and this is equal to, and we had defined these terms earlier in the last class. This, if you do the lumped parameter analysis of the system, this is equal to RA square plus XA square divided by RA plus rho naught divided by 2S plus XA square. Now, we had defined all these parameters in the last class, but I will again explain them today. So, what is RA? RA is the acoustic resistance of this muffler, associated with this muffler. As sound goes into the muffler, it faces some resistance, and RA is the resistance which it faces. And what is the value? It is equal to, now it can have three possible values. Okay. Actually, it can have two possibilities. Now, this pipe, this thin pipe, either it can be a clean pipe, okay, it is just a clean pipe, or what I can also do is, if I zoom in I can, if I zoom in this pipe, so that I make its opening a little larger, so that I can draw clearly. Suppose this is the pipe, I can cover this pipe with a fine wire mesh, fine wire mesh. Okay. So, as sound goes in, it has to pass through this crisscross pattern of wire mesh, and what this does is, this acts as a resistor. This acts as a resistor, acoustic resistor, because it obstructs the flow of sound into the pipe. Now, I can have one situation where I do not have this mesh, I can have another situation where I have this mesh. So, if I do not have this mesh, so let us say when there is no mesh, then R A we had defined earlier, and there were two possible relations for that. So, R A, which is the acoustic resistance, is equal to 2 pi times frequency times rho naught divided by C, when wave number times A, and what is A? A is the radius of this pipe. So, this is diameter, K A is less than the square root of 2, and if K A is more than square root of 2, then this is rho naught C divided by pi A square. So, that is there R A. Now, that is the case when there is no mesh. If there is mesh, suppose there is mesh, then the resistance offered by this mesh will be very large compared to these values. Okay. So, we can neglect the contribution of these values, then I can write R A as, R A can be written as R S divided by pi A square, where, so this is the case when there is mesh. So, this is the situation when mesh is present. And what is R S? R S equals specific acoustic resistance, and people have calculated the value of R S for different sizes of mesh. So, I will give you the values of R S and mesh size. R S, so if I'll just make a table. So, mesh size, so if mesh size is 30, then the value of R S is 5.67. Now, what is 30? The number 30 means that in 1 square inch of area, there are 30 wires, 30 by 30 wires in each direction. Okay? It is a grid of 30 by 30. So, that means, so this 30 tells us how closely packed these wires are in the mesh. So, if the mesh size is 50, that is 50 wires per inch, then this number is 5.88. If this number becomes 65, then this is 6.4. 100, then this is 9.1, and 120, then this is 13.5, and if it is 200, which is very fine mesh, then it is 24.6. So, from this we can calculate R A. Now, we also have to find, so we know how to calculate R A, we also have to find X A. X A is the reactance. So, X A is acoustic reactance, and that is equal to 2 pi f m A minus 1 over 2 pi f C A, and we had defined these terms m A and C A. M A is the acoustic mass, C A is the acoustic compliance. We had defined these terms in the last class, but nevertheless I will again write it down, where M A equals rho naught L C divided by pi A square, and C A equals volume divided by rho naught C square, and what is LC? So, LC, so this, if the tube is L long, LC is the effective length of the tube, and that is equal to L plus L A plus L B. And if you remember last class's lecture, I had said that as air passes through this tube, there is mass of air inside the tube, but it also has to oppose some mass of air at this end and some mass of air at this end. So, this extra length we call it L A, and this extra length we call it L B, and L is equal to L plus L A plus L B, that is L C. And we had also finally discussed how do we find L A. So, if there is flanged end, for each flanged end we can say L A or L B equals 8 A over 3 pi, and if there is no flange, then L A or L B equals 0.613 L. So, with this we can calculate how much sound power is getting out of the pipe. If this ratio is 1, then my muffler is not at all effective. If this ratio is very small, close to 0, then my muffler is effective. So, we had also defined that transmission loss is equal to 10 log of 10 1 over 80. So, if 80 is small, my muffler is very effective and the transmission loss number will be high. Okay. So, this is there. So, these are the results associated with a Helmholtz side branch muffler having a Helmholtz resonator. Now, what we will do is, okay, so there is one more thing. In sometimes what happens is we have a pipe and we have a volume. So, there is some volume, okay, and we connect this volume by not just one small pipe, but several small pipes, So, then the question is, in this case what happens? So, in this case C A, it does not change because the volume of the muffler is same. But if these pipes are equal in length, then acoustic mass is what? It is basically acoustic mass associated with one pipe times number of pipes. Okay. Because the amount of air present in each pipe, we have to add those things. So, acoustic mass goes up, and finally, acoustic resistance R A 1. Now, this, and I will not go into the mathematical details of this, this is actually this is total acoustic resistance is equal to acoustic resistance of one pipe divided by number of pipes. So, this is just the inverse, because the units of resistance, acoustic resistance in this mathematics are actually inverse of the actual resistance. So, that is why we actually divide it by number of pipes. So, this is important to remember. So, now what we will do is, I think the time for today is over, but in the next class we will have a continuation of the discussion of this Helmholtz resonator, and specifically what we will try to do is we will try to solve one particular problem associated with a side branch muffler, and learned how to design side branch mufflers which use Helmholtz resonator. So, that concludes our discussion, and I look forward to seeing you tomorrow. Thank you.